boa tarde, good afternoon. It's a great pleasure to greet you all here today. As you know, Professor Moshe Vardi from Rice University in Houston, Texas, yesterday received the highest distinction from our university. And it's a great honor to us as well that Professor Vardi was the first computer scientist that was awarded the title of Doctor Honoris Causa from our university. Professor Vardi was born, raised, and educated in Israel, and currently he is the Karen Ostrom George Distinguished Service Professor of Computational Engineering and Director of the Ken Kennedy Institute for Information Technology at Rice University. He has received his PhD from Hebrew University in Jerusalem in 1981, and he is the author and co-author of over 500 articles, which so far have accounted for over 35,000 citations. He's also the author of 2 books, Reasoning About Knowledge and Finite Model Theory and Its Applications, and the editor of several collections and journals, and currently he is the editor-in-chief of communications of the SIAM, which is the flagship magazine of the Association for Computing Machinery. Professor Vardi received numerous awards, including 3 IBM Outstanding Innovation Awards, the 2000 Kurt Gödel Prize, which is given by the European Association for Theoretical Computer Science, the ACM Kanellakis Award for Theory and Practice, the LEAKS Logic and Computer Science Conference Test of Time Award, the ACM Principles of Database Systems Mendelssohn Test of Time Award, the ACM SIGMOD COD Innovation Award, the Blaise Pascal Medal for Computer Science by the European Academy of Sciences, the ACM Presidential Award, the ACM Outstanding Contribution Award, the Computing Research Association Distinguished Service Award, the IEEE Computer Society Harry Good Award, the European Association for Theoretical Computer Science Distinguished Achievement Awards, the Southeastern Universities Research Association Distinguished Service Award in 2013, and he also holds honorary doctorates from the University of Saarland in Germany and the University of Orléans, France, in addition to the Doctor Honoris Causa we received yesterday from our university. He also has been a Guggenheim Fellow, and he's the Fellow of the Association for Computing Machinery, the American Association for the Advancement of Science, the Association for the Advancement of Artificial Intelligence. He's also a Fellow of the IEEE, the European Association for Theoretical Computer Science, and he's had many accomplishments. And this year, he has just been elected as a member of the United States National Academy of Science, and he's also become a Fellow of the Society for Industrial and Applied Mathematics. So it's a great honor to have you here, Professor Vardi. Thank you very much for your time in Porto Alegre.
Thank you very much for this kind introduction. This type of lengthy introduction reminds me of a story about 3 graduate students at MIT that wrote a paper. And the first one had a footnote under his name, and it says AT&T fellow, received a fellowship from AT&T. The second one has a footnote, it says Hertz fellow because he received a fellowship from the Hertz Foundation. The third one had a footnote, and it says a jolly good fellow. So yesterday we had a political talk. Today it's going to be very much talk about mainstream computer science. So we're going to talk about P versus NP, which is considered the major open question in computer science. I mean, there are lots of important questions in computer science, but this in 4 characters you can express a problem has been major open problem now for the past 40 plus years. And also it is considered today a major open problem in mathematics. I mean, there is a $1 million prize for this from the Clay Institute. It's one of the millennial problems. A few years ago, in August 6, 2010, Suddenly, an announcement comes up. A researcher at HP Labs, Vinay Deolalekar, announced he has a proof that P is different than NP, and he published a 100-page manuscript with the proof. So there was a huge buzz about it. And what I'd like to try to do today is both give you a very quick background on what is the problem, remind everybody what the problem is, and also talk about the events that have unfolded and a bit of a theoretical explanation of what really was the claim and what happened with that claim. So what is this problem about? So here is this is a picture from a rally in Washington, DC. We're all in favor of equality, so P equal NP, equality now. But more seriously, this is a problem in computational complexity. So the phrase complexity theory is a bit ambiguous because there are people who do look at complex systems and chaos. That's a very different type of complexity theory. We're interested in computational complexity theory. And what this theory is focusing on is how hard it is to solve computational problems. Now, what is a computational problem? I will not define it. It's actually very difficult to define, but I'll give an example. So suppose you have a graph. How many people here are computer science? How many people not from computer science? From what disciplines? What's your discipline? Non-computer scientist? Computer engineering. Okay, good enough. Computer science and engineering, yes. So I assume you know a graph is a network. You have a set of nodes and a set of edges. And in fact, it is it's an amazing because it's such a simple model that it models a huge range of phenomena. You can always describe as, now we all talk about social network, but this was invented. I'll talk in a few minutes how it was invented. It models a huge range of phenomenon, and there are many problems that are solving problems about graphs. And two fundamental problems. One asks, is there a Hamiltonian cycle? Is there a cycle that walks on the edges and visits every node exactly once? This is a Hamiltonian cycle. And then is there an Eulerian cycle? And this is again a cycle through the graph, through the edges, but this one visits every edge exactly once. Two very similar looking problems. And what we want to know is how difficult is it to solve it? I want to solve this problem. Let's assume that these are big graphs. Okay, today we're talking about, graphs with many, many millions of nodes and edges. Can we solve this problem? Now, this problem arose, Eulerian cycle arose. Euler lived in a city, Königsberg. Königsberg was a city, a Prussian city. Today it's actually Kaliningrad, which is a Russian city in a little enclave of Russia between Lithuania and Poland. It's a little piece of Russia that is separate physically from mainland Russia. And this is a picture, a drawing of the city of Königsberg. And you see there are this river and it splits and there are 7 bridges there. And on Sunday afternoon, the citizen of Königsberg would love to go to a nice promenade. And somebody asked the questions, can you take a walk, start from some point and take a walk and cross every bridge exactly once and then go back to the initial point? So Euler, who was a famous mathematician, was asked if he can solve this problem. And Euler realized that the big piece of land are irrelevant. You can abstract every contiguous piece of land as to one node, and you get a graph. Okay? So every node here is simply a continuous piece of land, and the bridges become the edges. And so now the question is, can we do an Eulerian cycle on this particular graph? The answer in this case was no, you could not. Now, this is an example of a Hamiltonian cycle. Now you see a graph, and the blue path is the cycle, and you can really check that it visits every node exactly once. This is a Hamiltonian cycle. So the definitions are incredibly similar. Then the problem are very, very different. Now we're going to talk about computational complexity, and this is the cost of solving problems. And we're going to focus on the time. How many steps does it take to solve a problem? If you really want to be formal, you can define in terms of Turing machine. But it turns out that these models actually are very robust, and you can take x86 and how many instruction do you need to do to solve this problem? up to constants and polynomial, these are all actually equivalent. And so we want to know how many operations does it take to solve this problem as a function of the size of the graph. What is the size of the graph? Again, we'll take something very simple, number of nodes plus number of edges. This is the size of the graph. Now the complexity class P are the problem that can be solved in polynomial time, and that means the number of operation is n to the c for some fixed c. Many of the problems that we deal with in daily life can be solved in polynomial time. You want to know, is the number even? Well, that's very easy. All I have to do is check the last digits and see if it's even. Is the number square? More difficult. How many people here remember how to do a square root, longhand square root, like long division? I still was taught how to do it by hand. So if you go back and you reconstruct the algorithm, you'll see it's a polynomial time algorithm. Okay? Turns out, whether a graph is Hamiltonian cycle, Eulerian cycle, we also can do it in polynomial time. It's actually an easy problem. But what about Hamiltonian cycle? Okay, Hamiltonian cycle, they are very, very clever algorithms, but not in polynomial time. So in fact, if you do it naively, you'll have to try all the possible cycles through the graph, and then there are n factorial such cycles. That's a very, very large number. If you want to be smart, you can do it in 2 to the n. You have to do dynamic programming. And even to do it in 2 to the n, it's a non-trivial exercise to do it. It's not trivial to do it in 2 to the n. To do it below 2 to the n requires very sophisticated algebraic technique. But 2 to the n, if you think what it means, take, for example, a graph with n equal 200, then it will mean 2 to the 200. Now imagine you have a computer that is as fast as a computer can be. And that means that every operation is done in the Planck time constant, which is, 10 to the minus 35, I think, seconds or something like that. And imagine that you turn the computer on exactly on the Big Bang. Okay? So the computer now has been running for about 14.5 billion years. You still have not reached 2 to the 200. Okay? These are very, very large numbers. So of course the questions that we would like to know, maybe we're just not smart enough. Maybe there is a better algorithm that does better. So the question is Hamiltonian cycle in polynomial time? Is there an efficient algorithm to solve polynomial time? Now, of course, there is a little flaw in the model, and the flaw is that polynomial is n to the c, so for some fixed c, maybe c is very large. Of course, if c is 1, 2, 3, we're happy. What happens if c is 1,000? Let me come back to this point towards the end. Now, people made an observation about 40-something years ago, that there is something about Hamiltonian cycle which is hard. It's hard to find it, but it's very easy to check it. If somebody give me a particular path and say, this is a Hamiltonian cycle, it's very easy to check it. All you have to check is that you start at the beginning, you go back to the same node, you visit every node exactly once, you walk on edges, very easy to check. So it turns out there are many, many, many problems that seem to be difficult to solve, but if you give me a proposed solution, very easy to check. Let's take, suppose I want to solve, I have a bunch of integer inequalities. Solving, difficult. But if you give me a solution, all I have to check, the inequalities are satisfied. So there are many, many, many such problems. In fact, tens of thousands of problems. There seems to be something very fundamental. The property, easy to check, is a very fundamental property. Okay? And so people say, let's define this as a complexity class. Let's define all the problem where they have short solutions. Here the solution is simply a cycle, and it's easy to check the solution. And so this is the class NP. So now we have these two classes. P is the class of problem that can be solved efficiently. You can discover a solution. And NP is a class of problem where you can check solution. And so the open question is, are these two classes the same or not? Is checking easier than discovering? Of course, our intuition is, of course, checking is much easier than discovering. Checking is easy. Okay, think about it. You all are going to leave at the end of the talk, and you say, well, Vardi did a good job, Vardi did not do a good job. But it doesn't mean necessarily you could have done a better job. So checking is easy. On the other hand, this is just intuition. So why do we think the checking is easy? Imagine we have a metaphor, finding a needle in a haystack. Of course, if I point you and says, here is the needle, checking is easy. Finding it is hard. Checking Sudoku is easy. Solving Sudoku may be hard. Coming up with proof is hard. But checking proof, if they're well written, should be easy. So in spite of this very clear intuition, it seems almost obvious that P should be different than NP. The checking is easier than solving. We still don't know whether P equal NP or not. Problem is still wide open. Now, suppose that P is different than NP. Okay? What are the consequences of this? If P is different than NP, that means that we actually have a lot of difficult problems. Okay? RSA, we cannot break RSA if P is different than NP. Okay? But why is it so important to prove that P is different than NP? Why is it so important to prove it? Because if we cannot prove it, then maybe it seems that we are missing something very fundamental if we cannot prove it. And furthermore, if we cannot prove it, maybe someone else, some evil agency, you can say the Chinese, the Russian, NSA, whatever your evil choice for evil agency, maybe they can break it. So we think that RSA is safe, but they can actually break it. Okay, I mean, in fact, when the whole NSA scandal broke and Snowden leaked all these documents, one of the big questions was people wanted to know, did NSA break RSA or not? And at least so far, from all the documents that have come out, NSA has not yet broken RSA. Okay, so we think that RSA is still safe. What about the possibility that P equal NP? Mathematically, it's possible. Scott Aronson, a famous theoretician at MIT, wrote, if P equal NP, then the world would be profoundly different place than we usually assume it to be. There will be no special value in creative leaps, no fundamental gaps between solving a problem and recognizing the solution. Everyone who could appreciate a symphony would be a Mozart. Everyone who could follow step-by-step proof would be a Gauss. So if P equal NP, then the good news is that all these problems in optimization that suddenly become trivial. Okay? What do you do? I don't know. But all these problems become very easy. Okay? On the other hand, it would mean that RSA is not safe because we can do factoring and we can break RSA. And so, the wide belief, if I had to do a poll here, what do you think? Most people say, no, we think they are different. Why do you think they are different? Well, that's because the professor told us. Okay? But we really don't know whether P is equal to NP or not. It's actually conceivable that P is equal to NP. And what would take to prove it is discovering a very, very clever algorithms that so far have not been discovered. But we need to remember the linear programming was open from the mid-40s until about 1980. So for 35 years. And then suddenly this guy that nobody heard of before, Hutchin, comes with the ellipsoid algorithm. And suddenly we found out the linear programming is in polynomial time. So it's conceivable that somebody will come up with a clever algorithm and prove that P equal NP. Now we can make the problem sharper by defining the so-called NP complete problems. And the term is a little misleading, but really what it means is the hardest problem in NP. And one of the fundamental results that we know now is that Hamiltonian cycle is NP complete. It is as hard as any other NP problem. And that means gives us an amazing color, P equal NP, if and only if Hamiltonian cycle is in polynomial time. So if you're trying to prove that P equal NP, all you have to do is solve Hamiltonian cycle. And there's one guy in Canada that keeps trying to do it. And about every couple of years, he publishes a new paper proving again Hamiltonian cycle is in polynomial time. And it's always buggy, but he keeps trying. Okay? You give him A for effort. It turns out there are thousands of problems that are NP complete by now. People started, we will see a little bit the history, but now there are thousands of such problems. It's enough to prove that one of them is in polynomial time, and the whole thing collapses. And so it seems that in this case, the attackers have an advantage. All they have to find is one problem, choice in polynomial time, and we've collapsed P and NP. Okay. So a little bit about the history. So people start writing programs roughly in the mid-40s. There was the ENIAC, it's 1946. And then by the early 50s, this became a business tool. Businesses start to write programs for insurance companies and banks. And at the same time, people discovered that some problems seem to be more difficult than others. And the beginning of this research effort of complexity theory is actually in the Soviet Union. They saw that there are some difficult search problems, and they tried to prove that they are difficult, but it was not successful. And finally, the concept of NP completeness was introduced by Steve Cook in 1971. And he proved that Boolean satisfiability is NP complete. So we have one problem. And then Picard published next year. He realized that, in fact, there are several problems can be shown to be NP complete. And they are all, in fact, equivalent. All these problems are equivalent. And independently, Leonid Levin, a year later, but completely independently, really had the same results from Cook and Karp. And in one paper with 3 pages, an amazing paper, but 3 pages, he was able to squeeze to show that there are 6 NP-complete problems. In 1979, the book by Gary and Johnson came out, and that kind of, even though it was just a textbook, it was really revolutionary because the theory was still young. I mean, now it looks to you that it happened in the Middle Ages, but remember the first paper in 1971. By 79, we have this paper by Gary and Johnson, still a very nice book, and they popularized the theory. Became very well known. The theory became very well known. And in 2000, the Clay Institute announced $1 million award. There is a check with your name waiting for it. Okay? Just solve the problem. Now, there was a little debate at the beginning about terminology. There were various proposals. And Knuth published a paper in 1974. He called it a terminological proposal. And he came up with all kinds of terms. It's really beautiful to see. It was very imaginative. How to call the hard problems arduous, bad, costly, difficult, exorbitant, exparent, formidable, heavy, Herculean, impractical, interminable, intractable, obdurate, perarduous, polychronious, prodigious, Sisyphean, tricky. And at the end, we end up with NP complete, NP hard and NP complete, which are not necessarily the most obvious terms, but they became popular, so now we are stuck with this terminology. So here is a quote. So now this is the background, and now we're getting to Deo Lalica. So many people heard about this on August 8, 2010. This was a Sunday afternoon. The blog comes out, and I've heard about it a couple of days before, but the blog comes out. I mean, somebody in fact sent me the manuscript on the Friday before, but suddenly I'm famous because here's the blog and describe the claim and says at the highest level, he, Deo Lalica, is using the characterization of polynomial time by a finite model theory. This proof uses the beautiful result of Moshe Vardi and Iggy. So this is, you know the phrase 15 minutes of fame. So here I got my 15 minutes of fame there. And what is the theorem? I'll read you the theorem, and I'll spend now a few minutes time to explain it. So the theorem says on order structure, the relation is defined by a first order formula plus the least fixed point operator if and only if it is computable in polynomial time. Don't worry that you cannot understand it. I'll try to make some sense of the theorem. This is really one of my earliest papers. It's a paper that I wrote. I did the work actually as a PhD student, and it's one of the very first papers I published as a postdoc. I think it was my second paper as a postdoc. And the paper is sitting there now, since then, accumulating citation. Now it has over 1,400 citations. So it's one of my claim to fame, so to speak. But if this, as much as 1,400 citations are important, if this theorem has been used to prove that P is different than NP, I'll receive many, many more citations, okay? So I was very excited when the claim came out. So now we need to explain, because I know the theorem is a bit of gobbledygook, so let's explain what the theorem says. Some terminology. What is a relation? A relation is a set of tuples of elements. So you're familiar with a binary relation, which is a set of pair. Ternary relation is a set of triples. And more generally, you can talk about k-ary relation, which is a set of k-tuples. Model theory is a branch of mathematical logics, and it deals with with the logical theory of mathematical structures. So we deal the connection between, essentially between syntax and semantics. Okay, this is the core of model theory. And model theory is a very classical, by now it exists since the 1920s. And in the 1970s, computer scientists and logicians start to say there's something special about computer science. Almost all the structures that we care about are finite. And so they came up with a variation of model theory in which they're looking at finite structures. This became known as finite model theory. Okay. So now, I'll do a very, very quick introduction to model theory. So we have to go back to the 19th century. In 1879, Gottlob Frege publishing a small book called Begriffsschrift, in which he proposed what became known as first order logic. And the question that you want to answer is, what is the language of mathematics? And he shows that in very, very different mathematical sub-disciplines, we're really using the same basic language. And what is the basic language? We have objects. For example, in number theory, the objects are numbers. In geometry, the objects are points and lines and circles. And we have relationships between objects. 2 is less than 3. 2 lines being parallel. These are all relationships between objects. We have operations on the object. 2 plus 3 is an operation. We have Boolean logic, and or not implies. And we have quantifiers. We say for all and there exist. And so what's special, this is considered to be a milestone in the history of logic, because somebody actually proposed logic as an underlying language of mathematics. And the whole movement became known as logicism, base mathematics on logic. And we can also take the Aristotelian syllogism, and it says all men are mortal, all Greeks are men, all humans are mortal, all Greeks are human, things like that. And now you can actually write it in a very rigorous syntax. If you want to say all men are mortal, it really means for all x, if x is a man, then x is mortal. And now I can write it for all x, and the inverted A says for all x, man of x implies mortal of x. Okay? So now we have a rigorous syntax to talk about properties of, in this case, of mortality, if you want. And we are going to look at, we are going to look at define first order logic on graphs. So in first order logic on graphs, we have variables, which are, they represent nodes. And atomic formula E of xy said there is an edge from x to y, and x equal y said that x is equal to y. And we're going to form formulas from these atomic formulas using Boolean connectives and quantifiers. So let's see, both. I have to aim at Lewis. Okay. Now I find the algorithm. Okay. Let's look at the following formula. P1. It says that the node x, which represents, it's a node, x represents the node, has at least two distinct neighbors. So I said there exists y and z, and not y equals z, so they are distinct. And there's an edge from x to y and an edge from x to z. Or I would say is that x and y are connected by a path of length 2. So I would say there exists a z, and a path from x to z, and a path from z to y. So now I can describe properties of nodes. Now, if you have properties of nodes, that means you can think of formulas as queries. You can think of phi1 as if it computes the set of nodes that has at least two neighbors, distinct neighbors. And you think of phi2 as compute the set of pairs that are connected by a path of length 2. So think of it, suddenly logic become a query language in which you write queries in a declarative way. I don't tell you how you compute this. I just say, here are the properties, give them to me. And this approach of writing queries in a declarative way ends up being the basis for SQL, which is declarative language. You express properties of relations, and the database has to compile it into an actual imperative program. So formulas can be thought as computable queries. So what does the theorem, the Immermann-Vardi theorem says? It says that polynomial time computability is equivalent to computability by iterating positive first order queries. So I just told you what are first order queries. I'll have to explain to you positive and iterative. But put this aside for a minute. What's people like about the theorem, I guess that's one reason you get so many citations, because it talks about polynomial time, but usually you define polynomial time in terms of Turing machine and operations. And here, there's no Turing machine, there's no polynomial. They say, where is the polynomial here? There's no time. It's a purely logical description of polynomial time. So to tell you that there is something fundamental polynomial time, which is beyond just saying you do polynomial number of steps of a Turing machine. So you can think of it as a very abstract description of what is P, and it says that P is something actually very robust, much more than just the definition that we gave before. So we need to say what is positive. So the formula phi2 that I gave you before, negation never appeared in that formula. It said there exists a Z such that there is an edge from X to Z and an edge from Z to Y. So that's a positive formula. In contrast, here is another example. It says that X and Y are connected by an incomplete triangle, and this said there exists a Z, an edge from X to Y, an edge from X to Z, but not an edge from Y to Z. Here I say not. That's not positive. Okay? There is something negative about this. And positivity is important because it has the feature that if something is positive, the more facts are true, the more things will become true. It's monotonic. On the other hand, if you have negation, if I suddenly if I add an edge from Y to Z, suddenly the property is not true anymore. So positivity guarantees monotonicity, which is very important. And now, so we define positivity, and we need to define, I'll give you an example also of what does it mean to iterate first order. So to do that, I'll remind you what is colorability. So to color a graph, you take the graph, and you assign a color, which is you have k color, you assign a number between 1 and k for every node. And the condition that you are requiring is non-monochromicity. Nice word. Non-monochromicity. And he says the two adjacent nodes do not get the same color. And this, of course, comes from coloring maps, where if you have a map and you want to color it, you should not use the same color on two neighboring countries because that will be confusing. So you want neighboring countries to have different colors. And this gives rise to non-monochromicity. And given a graph, we want to know, can you color it using K colors? And there is a beautiful feature here that if you ask the questions about 3 colors, this is 3 colorability, it's already NP complete, but 2 colorability is in polynomial time. In fact, I will show you how to do 2 colorability by iterating positive first order sentences. So here's an example. This is a 3 coloring of a graph. You see I'm using red, green, and blue, and you can see the 2 neighboring edges, 2 neighboring nodes never have the same color. So there is a easy lemma to prove that a graph is 2 colorable if and only if there is no cycle of odd length. And it should be fairly obvious because if a cycle of odd length, we're going to start black, white, you'll go around and you'll have a contradiction. And it turns out this is the only thing that you need to worry about. So now we need to write a logical description of this. We need to identify all odd cycles. Okay? So here is the logic. It says there is an odd path between X and Y. There is an edge between X and Y. Right? Because this is an odd path. It's one edge, so it's odd. And the second rule says there is an odd path between X and Y. The arrow says if, there's an odd path from X to Z, and then an edge from Z to W and an edge from W to Y. So I basically first catch all the one of length 1, and then I add 2, and I catch everything of length 3, and then I keep counting this way. So these are the 2 rules that by iterating them enough times on a given graph, you can compute all the odd paths. And finally, I will have a rule that says it is not too colorable if there is an odd path from X to X, which is an odd cycle. So by writing very simple rules, in this case you see in positive first order logic, in this case even with very few quantifiers, I can compute non-2 colorability, which is the complement of 2 colorability. So this is an example of that something is polynomial time, and indeed you can compute it using first order logic. And so remember, the theorem said that everything in polynomial time can be computed in such a fashion and vice versa. Now, how did the Olalekar use it to prove that P is different than NP? So he used, first of all, another connection with logic and complexity, which goes back to Cook. So, what is the Cook-Levin theorem? The Cook-Levin theorem look at Boolean satisfiability. So in Boolean satisfiability, we're getting a Boolean expression in terms of and, ors, and nots. And we have to find an assignment that will make it true. So here is an example of a Boolean expression, not x1, or x2, or x3, and not x2, or not x3, or not x4, and or x4, and so on. In this case, if you choose x1 to be 0, and x2 to be 0, and x3 and 4 to be 1, you can check it very, very easily that the whole thing becomes true. And the question is, given such an expression, is there a satisfying assignment? And Cook and Levin proved that this is NP complete. So this is the Cook-Levin theorem says this is NP complete. Now there is a physics perspective on satisfiability. So physicists are also interested in satisfiability. And they think of it as in terms of energy states. So for them, they look at the literal. So let's define the literal to have a positive or negative variable. And a clause is a disjunction of literals. So if the clause is satisfied, the physicist says it has a low energy state. They would like to bring every system to a low energy state. And if it's unsatisfied, then the energy state is high, it's 1. And so if you have a formula, its energy state is the number of unsatisfied clauses. So what we call the satisfiability problem, the physicists say, does it have a 0 energy state? So this is the kind of the physics view of satisfiability. Now, in particular, we can look at satisfiability and look at how many variables appear in every clause. And this we call it K-sat, where every clause has precisely K literal. So 2-sat, every clause has precisely 2 literals. And 2-sat, that's the 2 colorability. 2-sat is in polynomial time. And for any bigger K, it becomes NP complete. Now, again, inspired by statistical mechanics, people say, what happens if we have a random system? What is the random system? Let's fix the number of variables. And let's fix the number of clauses. And the important parameter here is the ratio of clauses to variables. And we call it the density of the problem. And so we're going to fix this ratio. We're going to fix a particular ratio. And now we're going to choose the clauses at random. And so now we're going to take n and m to the limit. We're going to take bigger and bigger sets of clauses, but fixing the density. So, and the physicists think of the density as the temperature. So what happens if you have very low density? If you have very low density, you have very few clauses. If you have very few clauses, it should be very easy to satisfy the problem. So you have low energy state. And if you have a lot of clauses, then it will be very difficult to satisfy all of them. And therefore you expect to be unsatisfiable and this will be a high energy state. Now people have done lots of experiments. And what we see in the experiment is the following. There is a phase transition. There is a density in which suddenly you flip from satisfiable to unsatisfiable. For example, here's the picture for 3 satisfiability. At the beginning, the very low density, the formula is satisfiable with very high probability, with probability 1. And as you go increase it, it starts to decline, and then it goes to 0 for high. So this by itself is not surprising. It's very intuitive. Very few clauses you expect it to be satisfiable. Lots of clauses you expect to be unsatisfiable. What is surprising, that as you take now the n, the number of variables, and you increase it, the step function become sharper and sharper and sharper. And so the belief is that in the limit, it will be a step function. Now, for 2-sat, people were able to actually prove it. That density 1 is a phase transition point. Below it, it's satisfiable. Above it, it's unsatisfiable. For 3-sat, empirically we know there is a phase transition at density 4.26. Why 4.26? That's what nature tells us. And it is still a major open problem. Can you prove analytically this is the case? And by now, 25 years, people have been studying this connection between statistical physics and complexity theory, and many papers have been written about it. Very fascinating research area. So now we get finally to Deolalikar. So Deolalikar paper claimed that 9 sat cannot be in polynomial time. Okay, not 2 sat. Now 2 sats we know is in polynomial time. Couldn't quite show it for 3 sat, but he showed it for 9 sat. Why? Here is the crux of the argument. He said if 9 sat is in polynomial time, then by Vardi theorem, you can express it by iterated positive first order logic, which we call least fixed point, okay? LFT. Iterated positive fixed point. But then he analyzed this iterated positive first order logic, and he combined it with what is known about the statistical properties of the solution space to this problem. I said there's been 20 years of research looking at random problem, and he showed that these two are inconsistent. The statistical properties are inconsistent, he claimed, with iterative positive fixed point logic. So this was a contradiction, and therefore P cannot be, therefore it means that 9 sat cannot be in polynomial time. So this was the 100-page manuscript that he released. That's the crux of the claim. Now, this created a huge buzz. Now, it is not surprising that we will be excited by a serious claim that P is different than NP. What is somewhat surprising, why was this taken seriously? Because if you want to find out about claims that P is equal to NP or not equal to NP, about every week somebody is making such a claim. It's a big world out there. A lot of people think, I'm going to be famous, I'm going to solve this problem, and they solve it, or so they think. So there is a website now that enumerates all the claims. Half of this goes to equal and half goes to unequal, and they're all wrong. Okay? So, in fact, there is a place, there is a place you can deposit paper, archive.org. Anybody can deposit papers, and people, every other week, somebody deposits a new claim in one way or another. Now people start to send them to me. Please check it for me. I said, well, maybe some other life. So why was this taken seriously? Now, this is now a social question. I can speculate. I don't have a definitive answer. Why was it taken seriously? It helped that he was not somebody in the middle of nowhere. Okay? I mean, this is, as we say, as remember from 1984, right? Animal Farm. All animals are equal, but some animals are more equal. So he's come from a very respectable research lab, HP Labs. He had the title, Principal Research Scientist. Title also helps. Okay? So there was one reason why people did not dismiss it. The paper was nicely formatted in LaTeX. That counts a lot. Okay? Usually if it's in Word, you almost can be sure that it's not correct. Right? I mean, it depends on, I get papers now, and I can almost make editorial decision by the email address. If I get a paper from someone whose address is hotmail.com, I can reject it immediately. Now, Steve Cook, who for us is the founding father, right? He is the Moses or Jesus, whatever you want to call him, of this field. He looked at it and he says, wow, this looks like this is a quote. This appears to be a relatively serious claim. And then there was a beautiful connection. Complexity, logic, statistical physics. People wanted it to be true. And Richard Lipton, who is a very respectable complexity theorist and very influential blogger in the theory community, blogged about it on that Sunday. And then the blog got /dotted. Anybody here knows what is /dot? It's a major website for kind of the techie community. And if you get /dotted, if you're mentioned there, suddenly tens of thousands of people are paying attention to what you're doing. So it's like going on news o'clock on TV. I mean, it's the equivalent of the 6 o'clock news in the techie world. So suddenly it's become a sensation. And the Deolalikar got his 10 days of fame, so to speak. Okay? So it took about 10 days for the proof to be completely discredited. So on August 6, he sent it out to 22 people and put it on the web. So this was a Friday afternoon it first came. The first blog was on Saturday, but the more important blog was by Lipton on Sunday, and then it got slash-dotted, and bam, the whole world exploded. By Monday, somebody already wrote a Wikipedia article about Deo Lalikar, and by Tuesday, somebody established a wiki so people can discuss the proof, and hundreds of people participate in discussion, including field medalists, very respectable mathematicians. They say, wow, this is exciting. Let's figure out what's going on. On the following Monday, there was a blog about it in the Communication of the SIAM by Lipton. The following Tuesday, an article in the New York Times. But now we can count the 10 days. The 10 days are over. Okay? 10 days are over. So in about 10 days, by the time the article appeared in the New York Times, already become clear that this was completely wrong. So what was wrong? What was the flaw? So he used the Imam-Vardi theorem, but he misused the Imam-Vardi theorem. He really made a mistake in using it. And people were able to show that his proof really does not distinguish between tractable and intractable cases of KSAT. What is a tractable case of KSAT? So we normally think that KSAT is, for K greater or equal than 3 is intractable. So there is a tractable case. In the tractable case of KSAT, we replace all the disjunctions, all the ORs, all the inclusive ORs. All we have to do is replace them by exclusive ORs. So you're still talking about KSAT. All the clauses have K variables, but you replace all the ORs, which are inclusive, by exclusive ORs. Why this becomes tractable? Because if you just think about it a little bit, this all become essentially equations modulo 2. What XOR does is simply does addition modulo 2. So suddenly this become a bunch of linear equations modulo 2. You learn in high school how to solve linear equations. If I told you it's modulo 2, no problem. Just do Gaussian elimination, do the same thing you do for linear equations. Just do it, everything modulo 2. So this is called the affine KSAT. And affine KSAT is tractable. It's in polynomial time, just Gaussian elimination, high school problem. But turns out if you look at from a statistical physics point of view, the affine case and the general case behave the same. The solution space geometry, what people call the geometry of the solution space, is identical. There's not much difference between them. So, and Deo Lalikar was relying on the geometry, on these statistical properties. But his proof could not distinguish between the affine case and the non-affine case. And people say that's an obvious, immediately you didn't even have to find a bug. Because essentially he proved that this problem is not in polynomial time. And therefore we know that this is wrong. So the proof collapsed. For a while, people still try to see, does it have any value? So let's see what actually happens. So here is as we saw what happened. The first draft was circulated on August 6, which was a Friday. People start commenting on it, and he responded to some of the comments, and he issued a second draft around somewhere between August 9 and 11, and then a third draft by August. The third draft existed for several days. On August 17, he removed it from his website. Okay, he removed from the website, and the problem said open. And here's what Wikipedia says about it. The general consensus among theoretical computer scientists is now that temporal proof is not correct, nor even a significant advancement in our understanding of the problem. Just to contrast this with another very famous claim, which was Fermat-Last theorem. Okay, so Fermat-Last theorem was announced. The solution was announced by Andrew Wiles, I think in 1993, if I recall. He gave a talk in Cambridge, at Newton Institute. He announced that he solved the problem, gave a talk. Of course, everybody was paying attention. And then people found a major hole in his proof. Big hole in the proof. And he was under, of course, some tremendous pressure. He and one of his ex-PhD students spent 2 years. They were able to fix the holes, and by now they are immortal, right? But here, people saying there's nothing there. It just completely evaporated. It's such a basic mistake that nothing was left, not single progress. It's not, oh well, if we combine something else. There's nothing was gained from this proof. Now, Deo Lalikar himself, I don't know where he is today. He disappeared. You Google him, I cannot find him. I don't know what happened to him. In 2013, which is 3 years after the incidents, he was still at HP and he was still defiant. Here is what his website said in 2013. He said, the preliminary version was meant to solicit feedback from a few researchers as is customarily done. It illustrated the interplay of principles from various areas, which was the major effect in constructing the proof. I fixed all the issues that were raised about the preliminary version in the revised manuscript, clarified some concepts, and obtained simple proof of several claims. Once I hear back from the journal as a part of due process, I will put up the final version on this website. So he submitted to some journals. I kind of hear from half year that all the papers have been rejected from many journals. And I don't know where he is today. Is he around here? He is not in HP anymore. I just before coming here, I tried to go back and to see what he's saying now. He's not in HP. The webpage disappeared. Now you still can find press releases by HP. HP made such a big deal about this. And now he just, mystery. I don't know what happened to him now. So I want to finish by kind of thinking about P versus NP. So there is a cliche that I heard it probably as a freshman in college. One of the graduates asking, what is the difference between theory and practice? And I didn't have a good answer. He says, you need to understand. In theory, they are the same, but in practice, they are very different. Okay? This is an old joke. So, from a theoretical point of view, P versus NP is a very important question because it's our basic understanding of the mathematical concept underlying complexity theory. But from a practical point of view, the problem could be resolved either way with no impact on practice. Why? Suppose that somebody proves tomorrow that P equal NP. So we say, oh, you can break RSA. Nonsense. To prove that P equal NP, you could prove that all of NP is in 10n to the power of 1,000. Complete impractical algorithm. Nothing useful. You cannot do anything with it. Okay? Differently, you could prove it's conceivable that P is different than NP, but NP is contained in n to the log n. Okay? This is not polynomial because it's not a fixed exponent. But my major was in physics, and I remember that when I was a freshman, one of the PhD students told us, what is the limit of log n when n goes to infinity? We are not idiots. He said, of course, it's infinity. He said, no. In practice, it's about 50. So to think of numbers that will give you the log is bigger than 50, the numbers are just so large that in reality, log n is less than 50. So an algorithm with a complexity of n to the log n could be a very practical algorithm, even though it's not polynomial. And so we could resolve P versus NP with no practical impact one way or another. So this is one thing why P versus NP is a very important problem, but perhaps maybe not as important as people claim it to be. It will not really have as dramatic impact as people claim that it will have. And here is another thing I thought I'll tell because I like it very much. This is about theory, practice, and programming. Theory is when you know something, but it doesn't work. Okay? Practice, something works, but you don't know why. And programming combines theory and practice. Nothing works, and you don't know why. But to me, the really very fundamental question is NP really hard? Or NP really described to us hard problems? Okay? So, when some of us were still young and we are thinking about NP, SAT was a scary problem. SAT was considered to be a very hard problem. SAT, you have to stay away from SAT. It's a dangerous problem. Okay? But today, in fact, we know that SAT is a difficult problem because you can construct synthetic benchmarks with only a few hundred variables, and they are very, very difficult to solve. But in practice today, we have very, very good SAT solvers, and they can solve problems with millions of variables. Millions of variables. So it's a really hard problem. It's not so clear. Yes, there are very difficult SAT instances. There are very easy SAT instances. And we really don't know when is that hard and when is that easy. And it tells us that the theory that we have is not rich enough. It does not tell us really what are the hard problems and what are the easy problems. And that's what we need from the theory, is a guidance, what is hard and what is easy. And right now, I think it's a beautiful challenge for theoretical computer science to give us a deeper understanding of the distinction between hard and easy problem. Thank you very much.
Thank you, Professor Vardi, for your fantastic talk. So we have time for a few questions. If you want to raise your hand, it's not a problem. This is a very nice professor. So if you don't have a question, I will do the honors. So I was noticing at the end that you mentioned the industrial use of SAT solvers, right? And SAT was a scary problem, and it is a scary problem for students and for some of our researchers. However, it has been tackled in industry and used by several IC designers, for instance. There are other fields of theory that people keep in producing results. However, but they are theoretical results, as you mentioned, and theory you define very well in slide number 39. And do you think that this approach that this researcher that has so far disappeared, using very interesting results from logic, some of results of yourself, results from complexity theory, and even results from physics? So the problem is so hard that we may need to prepare the researchers and the students better in order to solve if either P is or not equivalent to NP.
So P versus NP is almost, you can think of it as a problem either from God or maybe from Lucifer. Because the problem is toying with us. Okay? People have come up with all different lines of attack about it. And I've been involved. Trying to model theory, one of the reasons we developed it was a line of attack using logic and games. We are going to bring concept from game theory, and we're trying to do it. And the problem just laughs at us. You know, we attack it, and it's like impregnable wall. You go with everything, and you just fall back. Nothing happens. So really, it's an amazing problem. Mathematically, it's an amazing problem because we have made so little progress, and people have come out with all different lines of attack, and nothing so far works. The most recent one is algebraic geometry. Okay? How many people here really know algebraic geometry? Please raise 2 hands. What is it? Nobody knows algebraic geometry here. So there is this guy at Malmali, and he says that it's algebraic geometry is the key to resolving P versus NP. And the problem is that for most of us, if you said, okay, you convince me, what do I need to do? I need to now to spend several years studying algebraic geometry. So very few people are really taking this approach. It's a very formidable approach if you're going to do it. He's working on it. There are people debate whether the claim should be taken seriously or not. Algebraic geometry is the key. So we have tried to bring all kind of mathematical theories. People use logic, people use descriptive set theory, circuit complexity. So far, you know, I used to work in IBM with a very brilliant guy, Nick Pippinger. And I remember somebody was asking, are you working on P versus NP? And he said, no. Do you think it's not an important problem? He said, no, it's a very important problem. So why are you not working on it? He says, I don't have the dimmest idea how to attack the problem. And so right now, you know, you find very few people that say, well, we are really working on the problem because we really don't have good ideas how to attack the problem. So people have tried to use statistical physics and all kind of technology. If you look at some of the lower bound that people use in proof complexity, which is another line of attack, people use amazing, you know, people were forcing for technique, all kind of techniques in logic. But at the end of the day, I said the problem is just laughing at us. That's how I feel about it. Yeah.
Are there any other efforts that have proven useful for trying to categorize problem difficulty? because it seems that maybe intuitively we are taking the wrong approach to measure. I mean, when you look at sets, 2 set and 3 set look similar, but they are actually very different in terms of complexity. Are there any other attempts to
So there is a branch of complexity theory that's called parameterized complexity, and it looks at it tries to look at the problem and find more fine structure for the problem. Right now we're saying, okay, it's just a formula, and so you can think here that of the what we call the width of the formula, how many variables per clause, it's a parameter of the problem, and people have looked at different parameters of the problem. Okay. And there are some parameterization that actually make the problem tractable. So, for example, one is you look at the graph that corresponds to the formula. What is the graph correspond to the formula? You draw an edge between 2 variables if they appear together in the same clause. It's very easy. Given a formula, there is a graph of the formula. And now you ask yourself, how close this graph is to being a tree? Because as you know, you should know in computer science, trees are easy. Okay? You should remember that. Trees are easy. So many problems are difficult generally for graphs. For trees, they're easier. And not only they're easy for trees, they're easy for tree-like structure. And the technical concept is tree widths. So it turns out, if you take these formulas and you say the graph has to have bounded tree widths, which is essentially say it is tree-like, suddenly satisfiability become it's in polynomial time. And so there were some attempts to try to use this to explain why practical instances are easy. We have not found yet the right structure. Many people believe there is some hidden structure that will explain why industrial problems are easy. But so far we have not found this hidden structure. But that's my intuition. This problem must have some hidden structure. But so far it's a big open problem. We don't know what it is.
How is the procedure to check if a proof is correct or not? Because I think a few years ago there was a few trials, and now you mentioned that every week there is a new trial. So is there a committee or a web page that receives and the community check how it works?
There is a very simple procedure. They're all wrong. So, there isn't really a good process. Part of the problem is suddenly I get a manuscript with tens of pages. Somebody sent me, this is and I have to tell you, some of the people that send me the proof, you can tell there are all kind of clues that they are not quite okay. I don't want to say more, but there are some clues that are not quite okay. So if the same person send me every week a proof, okay? Okay, now this is a clue, and I don't want to spend every week reading the new proof and doing it. People, the truth of the matter is that there is a phrase, I think it was Carl Sagan, who's an astronomer, a very popularizer of astronomy. And he has a beautiful phrase that I use a lot. And he said, big claims require big evidence. The bigger your claim, the better the evidence you have. So, at least the nice thing about the Euler car, okay, and this is another explanation why the proof was taken seriously. There is a structure here that seems attractive until you find the flaw. Like you find a little thread in the suit and you pull the thread out and the whole suit falls apart. You say, wow, look at this, beautiful. You use the theorem, you relate to statistical properties. I mean, there was a structure that looks very beautiful. So when you see such a structure, you take it more seriously. Okay, so this is really, I want to show you the proof did not look crazy. Many of these proofs, you look at them and you say, wow, it's my job to go and find exactly where the error is. So most of the proof, people dismiss them out of hand. They don't even bother to check them carefully. Once in a while, something look, wow, this is more serious, and then people check it. But we don't have really, there's no easy way. You can't feed it to an automatic compiler that will check it. There is an attempt in mathematics to formalize proofs. There have been some cases. I mean, of course, the most famous one is the four-color theorem. I talked about graph coloring. Okay, but more recently there were some instances of proof that were claimed. There was the Kepler's conjecture, which is about packaging balls. And there was a claim that the intuitive way of packaging oranges, putting 4 oranges, put one in the middle, is really the optimal way in terms of density. And the paper was submitted to some journal of mathematics, and the reviewer spent 2 years on it. And it says, it's too complicated. We can't follow the proof. Too many cases, we cannot follow the proof. So they actually spent several years formalizing it in COP, in a theorem prover. And which gives us much more confidence that the proof is correct, because this theorem prover usually have a very small kernel that you have to trust. And you can read it, it's open, you can read it, few hundred lines that people can read and trust. After that, everything has to be extensible within the theorem prover. And so there is a whole effort now in the last few years of formalized mathematics, to take some of the more complicated theorems in mathematics and to say, well, you really convince us, you have to formalize the proof. And the tools are getting better. It's an interesting development in mathematics, whether we will requiring every proof should have a certificate in some sense. We're not quite there yet. We still write proof mostly the old-fashioned way. Clearly, obviously, and the like. Okay, thank you very much. There was another question.
This week, it was announced that there is a new result about the edit distance. Have you heard about it? And it relates the complexity of solving the edit distance in sublinear time with NP complete that.
This is very interesting. It's a paper that apparently is appearing this week in Stock. And I have not seen the paper yet, but I've read this news. And what they claim is, so this is a problem with polynomial time. But the best algorithm we have is quadratic. And the question was open for many years, can you do less than quadratic? So they use a stronger assumption that of the NP is different than NP. There is an assumption called the exponential time hypothesis, ETH. And the assumption is that satisfiability really requires exponential time. This is much stronger than P is different than NP. But what they were able to show, and I think this is a beautiful development, because we're talking about quadratic algorithm. They were able to show that if you can do it in sub-quadratic algorithm, then you can use it to do SAT in sub-exponential time. So now we have a way of proving that, and we have many such problems that have quadratic algorithm, and people have tried very hard to do better than quadratic, and we just don't succeed, and we had no tool to prove lower bounds. So what's nice about this is the first time somebody is using kind of heavy complexity theoretic tool to prove very pragmatic lower bounds on very simple problems. So it seems like a very beautiful result, but I have not seen the details of it. Okay, thank you very much.
Thank you very much. So just to close the session, thank you very much, Professor Vardi, for your time here in Porto Alegre. It's been an honor that our university gave you the title of Doctor Honoris Causa. Thank you very much to you all.